So we have the ball being shot up this way. We have some incline here. We know that because it's inclined, there will be, well, let's imagine the forces on the cart. So I'll isolate the cart. What are the forces on the cart? Normal force, meaning from the rails will be pushing on the cart, let's say this way. What else? Gravity, which pulls at the center. Okay. Yeah, so I want to worry about the cart just after the ball leaves, and then we'll watch it and we'll compare it to the ball after it leaves and see if we can understand why they get back together. So are there other forces on the cart? There could be some friction, which we're hoping is small enough as not to mess things up. So I'm going to ignore it. Okay, what else needs to go on my isolation diagram? Okay, direction for the acceleration, or a coordinate system. So it's not obvious what orientation I should use for my coordinate system, or is it? Should I make it horizontal so it respects gravity, or should I make it tipped so it respects the normal force? Tipped? All right, let's try that. Okay, so if this is my coordinate system, then isolating in the x direction, I only have one force. And that force is gravity. So I can decompose the force of gravity into the component that's parallel. Let's see, did I do that backwards? Let me make this nice and big. Yeah, so I have gravity coming down. I have this direction for x, and this angle for theta, and I want the component of gravity that's along this direction. So this angle here would be 90 degrees minus theta. And so the angle between gravity mg and my x direction is 90 degrees minus theta. So the component along of gravity along the surface would be what? The cosine of 90 minus theta, equivalently the sine of theta. So I would have mg sine theta is equal to mass of the cart is capital M, acceleration in the x direction. And I always cheat on these things, so let me describe the method of cheating again. If we just imagine that theta goes to 0, is there any component of gravity along the direction along the rails? And then the answer is no. So I need the trig function that goes to 0 when theta goes to 0. And so that gives me confidence that I have the right thing in sine theta. OK. Let me introduce, we're going to use it a lot. Let me introduce another notation for acceleration that is due to the character of the day, Isaac Newton. He wrote a dot over a symbol to mean a time derivative. And so if you have two dots, that means the second time derivative. And in calculus, you probably are used to seeing like primes. F prime of x would be a way of denoting the derivative. That's also Newtonian notation. Prime is sort of, it doesn't matter what the argument is. Dot is only ever used when we're differentiating with respect to time. But we do that a lot in this course in dynamics. And so we tend to use the dot notation. Okay. What about in the y direction? So in the y direction, we would have the normal force going up, mg cosine theta going down. That must be equal to m y double dot, except that what will happen in that direction? Nothing.
Not to the cart.
Okay, so yeah, not to the cart, because the normal force will just adjust itself so that y double dot is 0, unless the rails fail and it falls through the rails. Okay, so from this expression, we just could learn that the normal force will be equal to mg cosine theta. Okay, now we need to consider the ball just after it's left the cup. So we isolate the ball. And what are the forces on the ball? After it leaves the cup, just gravity. Anything else? None. Okay, so now I want to use the same coordinate system that I used up there. If I do that, then in the x direction, I'm going to get mg sine theta is equal to mx double dot. I should be careful here. This is for the ball, not necessarily the same as that one. And in the y direction, I get mg, and let's see, in the y direction, I'm going to have a minus cosine theta, and that should be m. Yeah?
Should we not technically have an F naught from when the...
He asks if we should have an F naught from when the ball was released. Good question. Do we need an F naught? I want to consider the time to start right after the ball loses contact with the cup. So now it only has gravity on it. So I've left off anything else, okay? Because they're basically in the same place at the same time until that happens, okay? So from this equation, I can see that the mass is irrelevant, and I get that the acceleration of the ball is equal to g sine theta. That's what it does in the x direction. What happens to the cart? Well, over here, I can cancel m, and I have x for the cart, double dot, is equal to g sine theta. So the acceleration in the x direction is the same. What about the initial velocity in the x direction? So if I were to integrate to get from acceleration to, if I integrate the acceleration with respect to time, I'm going to get the velocity. So that gives me the velocity as a function of time, which is gt sine theta plus whatever velocity in the x direction it had initially. I'm counting time 0 when what? The ball leaves the cup. So whatever velocity the cart had or the ball had in the x direction right at the time that the ball left the cup. And similarly over here, I can integrate x double dot dt, which is the integral of g sine theta dt, and that's g sine theta times t plus whatever initial value it had of velocity. Well, that's the same. So they move in the x direction together, and therefore when all the shooting matches done in the y direction is over, they're right in the same position in x. Does that make sense now to people? Okay, so this equation for v, and I could integrate again. What happens if I integrate again? I get the position as a function of time of the ball. That's the integral of x dot dt, which is the integral of gt sine theta plus vx naught and that will be 1/2 g t squared sine theta plus vx naught t plus whatever position the ball had right at the point of launch, which I'm calling t equals 0. So x naught. My chalk is done. And if I integrate over here, I'm going to get the same thing. And they started together, so therefore they're going to end together. Any question on that? Yeah?
So even if you elevated it to like 89 degrees, as long as the whole rail was long enough and tall enough and you started at the top, it would still.
Yes, so he's got a great limiting worry. Suppose that the rail ends up being basically vertical. Then we have a problem, right? Because it's given an impulse and the cart never moves in that direction at all. But if it were at 89 degrees, as long as the rail were long enough, we'd be all good. Okay? Good worry about a limit there. Yeah?
Just a clarification.
Yeah?
So when the cart is going down, when the cart and the ball is at the same initial velocity, however, when you propel it with some force,
Right.
you get an acceleration in the x direction, an additional acceleration in the x direction.
So he's asking when the spring fires and the ball gets accelerated in a short time, gets an impulse, the direction, because of the way we picked our axes, that's purely in the y, right? Okay, so what happens to the normal force on the cart while the spring is going skabroing?
Oh, it increases a bit.
It will have to get bigger. Okay, so it temporarily gets bigger and does what it needs to do so that the cart doesn't go through the rail. The ball comes up, but it's been accelerated and given an initial velocity in the direction y perpendicular to x. And so everything in x happens placidly together, and it affects both of them equally so that when the ball falls back down, it is in the cup.